I hope everyone can see the slides now. So many thanks for giving me the opportunity to talk about this very nice objects, and thanks for the organizers for the very nice hybrid meeting. I'm really enjoying it in place, and I hope people online are also enjoying it as well. Also, as this meeting is dedicated to Matt Wilson, I couldn't start my talk without mentioning him, as I worked with Matt during his PhD thesis time here in Exeter, and also later on I continued to collaborate with him in Belgium, and we observed some of these targets with aperture masking observations. So it was always a pleasure to work with him, especially here during his PhD thesis, but also to play some football in every Wednesday evening. So yeah, I just wanted to. He will be very missed. So yeah. All right, back to the science. So today I will talk about this evolved binaries, post-AGB binaries, and I will focus on their disks. And I will show you that these disks are very similar in many ways to disks that are seen around young stellar objects. And so one question that arises, so do they form second generation planets? So answering this question is of course very exciting, but I think to answer this question, we have to answer many other questions that can help us to understand this physics and also give some answers to planet formation processes around young stars. All right, but first, what are these bits? What are the post-AGB binaries? So here I show you a nature diagram. So you have luminosity against the temperature, and the post-AGB phase for a single. This is a track for a single star, one solar mass star, and the post-AGB phase is the most luminous phase of the life of the star, and it's after the giant branches. So you have the RGB and AGB phases, and it's before the planetary nebula phase and the white dwarf phases. And so this is for a single star, but if there is a companion that is close enough, when the more evolved star will become a giant, we'll have some interaction between the two stars. So you can have Röhrschloop overflow, you can even go through a common envelope evolution. It's not really clear what is the interaction mechanism here, but what we know is that it can end the giant branch phase earlier, because the interaction will strip the atmosphere of the evolved star, and the evolved star will go through this post-AGB phase earlier. So it will contract and will heat up and become a white dwarf. So the binary interaction interrupts the stellar track, but also produces a circumbinary disk. And this is what is very interesting in this target. And so those binaries we know around 100 in our galaxy and 200 in the LMC and SFC, where we know the distance, so it's much easier to get the luminosity of those targets. So how do we know that this binaries have disks? So, well, we look at the spectral energy distribution. So here you see the flux against the wavelengths. You see in the black the stellar photosphere that was fitted in the visible, and we see in red the infrared excesses. And there are two different kinds of infrared excesses that we see. We see a shell-like infrared excess that can be fitted with one single temperature black body, and a disk-like infrared excess that needs a series of black bodies at different temperatures, as you will have different dust at different separation from the central star. And when you monitor those targets with radial velocity, what you find is that around the shell-like SEDs, you never find a companion, but around disk-like SEDs targets, you almost always find a companion. So there is a very strong observational link between the presence of a circumbinary disk and a binary at its center. All right, so I will go through some of these properties relatively quickly. So there's a disk formation process, is the ejection of the stellar atmosphere because of the binary interaction, and part of the mass is bound to the system in the form of binary disk in the orbital plane. There's always inner binary. The central star is very luminous, so it's a post-AGB star, and evidence for accretion and outflows from, for example, large-scale ALMA observations. And the system are isolated, so there is no interaction with an environment as for young stars, for example, as was mentioned yesterday by Christian. Some disk properties, so there's this infrared excess that is disk-like, they are stable, as seen in the CO maps at large scale. We see Keplerian motion. The disk masses are quite high, so it's very comparable to what we see around young stars, 10 to the -3 solar masses. There's evidence for dust, some dust growth from speeds of data, but also some millimeter observations, spectral indices. And the disk lifetime is, it seems that it's very short because of the post-AGB phase that will be also very short. So everything that happens in this disk has to happen very quickly. And so why do we care? So these targets are were mainly studied for stellar evolution and mainly for binary evolution because there are some unexplained orbits. So after a binary interaction, we expect like two period peaks. So one for the common envelope evolution binaries that spiraled in, and one for wind interaction that widen the orbit. But what we observe is that the distribution of the periods is right in the middle. So there is something that we don't understand, and we think that this binary interaction may be the key to explain these orbits. These systems are also thought to be possibly progenitors of planetary nebula of these bipolar morphologies. But what we can also use this object for is for this physics and planet formation. This is something that interests me because I'm coming from the young stellar object community. And actually, it's a new laboratory because these disks are really in a new parameter space because of the disk lifetime, because of the stellar luminosity. And so we can test how the physical processes that we see in this young stellar objects are behaving around these binaries. So we have different time scales, and we also maybe have some first generation planets that survive the giant phase that can perturb the disk from the start. And so we can see if the dust grain growth, what is the time scale of dust grain growth in these disks? Can we see some substructures, and can they lead to planet formation? All right, so what are the scales of this disk? So this is an artistic impression of such a circumbinary disk. You have the post-AGB star here, the secondary here. We observe some jets around the secondary. And so basically the separation between the two stars is roughly 1 astronomical unit. The inner disk rim is at 10 astronomical unit because the post-AGB star is very luminous, so the sublimation radius is quite far. And the outer radius of the disk in the dust is around 100 or few hundreds of astronomical units. And so the typical distance to this object is 1 kiloparsec. So it means that 1 astronomical unit is 1 milliarc second. So we really need high angular resolution to resolve these targets to get the structure of the disk. And so we are very lucky because now we have all the facilities to do that actually. So for example, in the near-infrared where we see the binary and the inner disk rim, we can observe with the VLTI and with Chara, and we can resolve the very inner regions. Then in the mid-infrared with Matisse, we can probe the inner disk structure. And with ALMA, we can probe the outer disk structure in the midplane for the large grains. And even in scattered light with SPHERE, we can probe the disk surface in small grains and with GPI as well. All right, so it was a long introduction. So now I can I can present you some results. So I will start by showing you the results that we already obtained on this target. So the first image, and go to the VLTI surveys of these disks, and also talk a bit about the transition disks that we see around this evolved binaries. And then I will talk a lot about the observational perspectives because there is a lot of things that are going on and very exciting results that are coming. All right, let's start with the first image. So I'll focus on this one target, which is RS-08544-4431 that I will call now RS-08. Here you can see the radial velocity data. So it's a binary with a period of 500 days, a moderate eccentricity. And you see that there is a very nice disk-like infrared excess in the spectral energy distribution. And so we managed to get a very nice UV coverage using VLTI Pioneer. And this is the image that we get when we just use a monochromatic image reconstruction algorithm like MARA. So we are really dominated by the central star that contributes to 50 up to 60% of the emission in the infrared. And this is the only thing that we see, and it really covers the rest of the emission. And so we can remove the star using the Sparko approach. And when we remove the star, so we model it with a geometrical model, we see two things. First, there's the point source emission very close to the primary at the location of the secondary. And it's unexpected because the primary is a post-AGB star, so it's very luminous. And we do not have the contrast to see a main sequence star around this the post-AGB star. So what we think we see is that we see the accretion disk instead around the secondary star. And this is backed up by the fact that we see outflow around the secondary in H alpha time series. And the second thing is that we see this very nice ring, which is the inner rim of the circumbinary disk that is at roughly 8 astronomical units, and that is asymmetric. So you have one very bright side that is on the side of the post-AGB star that is illuminated by the very bright post-AGB star. And we have some another maximum here on this side that could be due to this binary interaction as parallel wave, for example. And we wanted to know more about this target, so we observed it with all the 4 telescope instruments on the VLTI, Perigee, Gravity, and Lattice. And I will just keep it very quickly. There will be a talk with by Ake Corporal later on this afternoon that will describe this observation and the redshift transfer model used to reproduce them. All right, so now what we wanted to, I have nothing on the screen, but okay, I will continue. So what we wanted to know is whether this IRASO8 system is representative of all the post-AGB binaries disks. And so we made a survey. So here there was a survey with MIDI and a survey with Pioneer and near-infrared. And here are the geometrical models. So these are not image reconstruction, but geometrical models that were fitted to the data. And so in the near-infrared, we mainly see the disk and the binaries in some of the cases. And here are the main conclusions that we had from this study. The first one is so there's this size luminosity relation for YSO that was shown by Karen yesterday, and it holds also for massive YSOs as shown by Evgenia yesterday as well. And so good news, it also holds for disk around post-AGB binaries that are here in purple. But there is a small shift toward larger sizes that could be due to either different grains mineralogy or a lower gas density at the sublimation, in the sublimation region. All right, the second main conclusion is that those disks are mainly continuous. So here in the, so there is a comparison of the size in the infrared, in the mid-infrared. In the yellow area, this is where you expect all the models with continuous disk with power law, temperature power law with radius, and you see that most of the targets are compatible with a continuous disk emission. And the third conclusion that we had is that the morphology of the targets is very complex. So we needed 10 or more parameters for most of our targets to reproduce both the visibilities and the closure phases. So we really need image reconstruction to get an unbiased view of the emission of these targets in the near-infrared. All right. And so this survey, especially the VLTI survey with Pioneers and near-infrared, were biased towards the targets that are that have an infrared excess, but it's not the case of all the targets. For example, here, AC HER, you see the spectral energy distribution, and it starts at 4 or 5 microns. So there is no excess in the near-infrared, but only at 4 or 5 microns. And so this target was observed with MIDI. It was deduced that the inner rim radius is at 34 astronomical units. And so this is 7 times larger than the theoretical dust sublimation radius. And the inner binary is only separated by 1 astronomical unit, as you can see, as you will see with in the talk of Narcis Anegus this afternoon, where he derived a nice orbit with Shara Mercake's observations. So what is causing this cavity? So first, we wanted to know if there are other objects in the galactic post-AGB stars that share similar infrared excess characteristics as AC HER or as the full disk of IRASO8. And so what we did, we made a color diagram, as also shown yesterday by Evan Rich for YSOs. So one color in the near infrared, one color in the mid infrared, and you see that the colors will be different for the two targets. And put everything on this plot. You see here the near infrared color, H minus KS, and the mid infrared color, WISE1 minus WISE3. And you can see that RSOA, the full disk, is located here, and there's a bunch of other disks that are similar around it. And here AC HER, so the disk with the large cavity, is located here, and there are other targets that are also in the same area in this color diagram. And so we put boxes in this color diagram in order to separate the different areas and try to understand what we are looking at. And here I plot the infrared excess, the median infrared excess for all the post-HB binaries, and the 25th to 75th, sorry, quantiles to show all the variations that there is in the infrared excess. And so if you look at this full disk SEDs, full disk object here, we see that the SED infrared excess is really close to the median infrared excess. But if you look at in the area where the transition disks are, so those with a large cavity, you see that there is no near infrared excess, but then a very large mid infrared excess. This is because the inner rim of the disk is directly exposed to the central star illumination, and then it's puffed up and it emits more in the mid infrared than for a full disk. And so then we made other boxes. I don't have time to go into the details, but you see that with the color diagram, you can really differentiate the different types of infrared excesses. It's a very nice tool. And so what can we conclude from this is that there is 10% of the disks that have a large cavity and that are reminiscent from the transition disks around young stars, because around young stars, we also find that 10% of the disks are transition disks. But there is more. If you look at the iron over H ratio on the post-HB star around full disk and on transition disk, we see that the stars surrounded by transition disk are more depleted in iron. And so this is not tracing the metallicity, but this is tracing the depletion of refractory elements on the surface of the post-HB star. So here you have the abundance of different elements with versus the condensation temperature of these elements, and you see that the volatiles are not depleted, but only the refractory elements are depleted. And so iron is located here, and this was interpreted as a mechanism, evidence for a mechanism that is trapping the dust, so the refractory elements in the disk, but is only accreted the depleted gas onto the surface of the post-HB star. So iron over H is tracing this. There are other tracers that also indicate this difference between the full and transition disks. And so there is something that is creating the cavity and at the same time trapping the dust, preventing the dust to be accreted onto the central star, but only the gas. And so the most likely hypothesis that we have until now is to put a planet here in the disk, and that will make that is filter the dust from the disk and will let only the gas to be accreted onto the central star. And what is interesting is that this is also seen around YSOs. So it's also seen around in Herbig stars, where it's easy to derive the surface abundance, as can be seen in Kama et al., for example. So it's something that is in common with young stellar objects. All right. And so now we want to know more, of course, about this disk. We want to confirm this hypothesis of transition disks. And we also want to know what is the morphology in the near infrared of this post-HB binary targets, because we may be model biased just by fitting chrometrical models. And so we started a VLTI large program to image 11 of these targets. So the large program is called Inspiring. It consists in 250 hours of observation with Pioneer and gravity on 11 targets. So the main goal is to retrieve the structure of the circumbinary disk, also to see how it reacts to the binary phase and see if we can redetect the secondary around other targets on RSO8. And we also develop a new methodology, a new image reconstruction algorithms that is called organic, that basically uses a neural network to learn the Bayesian prior in the image reconstruction directly from astrophysical models instead of using, for example, a smoothness constraint or a total variation. It gives very nice result in the image reconstruction, and it also helps to better reproduce the data actually. All right, and then we go from the image to the geometrical modeling and from the modeling to the radiative transfer modeling. And these are some preliminary images of some of the targets from this large program. So you see that we see some targets that have a double ring structure. We see some inclined disk, some even more complex morphologies. And if we compare these images to images of disk-round Herbig stars, we see that these ones are more resolved, even though they are further away. Because of the high luminosity of the central star, we still see the dust sublimation radius. And we are even able to make a imaging time series on IRAS-08 to see several epochs. So this is using Mira Sparkle. But if you use organic, you see that the blobs are going away. And you see that the part of the disk that is closest to the post-AGB star here in white is always more luminous. So I'll talk a bit more about this target at the EAS conference this summer if you're coming at the VLTI session. And there are even more orbits fitted from Chara at the Narcissus talk this afternoon. All right, this is for the inner regions, but what about the outer regions of these disks? So we made a survey with Sphere, Erdis, and Zimpel, and we got some preliminary images as well. And you can see that there's a lot of different structures around those targets. So you have like here, we are tracing the surface of the circumbinary disk. We have some ring morphologies and some more complex structures. We even have an arc, which is probably the inner disk rim here of one of the transition disk targets. And this is a study that is led by Katja Andries, a PhD student that is now at Macquarie University in Australia. And what do we see with ALMA? So this is, we also get some time with ALMA to study, to resolve for the first time the dusty disk around those post-AGB binaries. And this is what we see. So we see that we have millimeter-sized dust that is extended 100 astronomical units away from the central binary. We have some substructures, so that's very interesting to study. And here the white circle is the dust sublimation radius from the image that we see with Pioneer. So you see that we have all the different scales in this in observations. And actually, we have all the wavelengths as well. So we have the Pioneer image reconstruction, a geometrical model for gravity, Matisse at 3.5 micron, Matisse at 10 microns, the Sphere image and the ALMA image of this disk. So we can really model this target as with all these observations very precisely and understand the structure of these disks. We can also make the link with between ALMA and VLTI for all the targets. So here you see that we have this double ring structure. We think that the outer ring is above the disk midplane, and at large scale, we see with ALMA this bipolar structure with the wind, also a jet. And we can make the link between the Sphere observations and the Pioneer observation for other targets that have the same inclination, but a very complex structures in Pioneer that we still need to interpret. All right, so I'll finish with my conclusions. So I hope that I convinced you that the post-AGB disks are very similar to disk-round young stellar objects, but they also have some differences. And I think these differences are very interesting because we can study how a disk evolves in a very peculiar parameter space, and it can give answers on the time scales and on the of different processes in protoplanetary disks, including processes leading to planet formation. We start to see signs of planets that still needs to be confirmed. That is quite exciting. Of course, the origin of the planets is, if they are true, is unknown yet. And we started a thorough observing campaign to uncover all the details of this disk to make a very precise comparison with the disk-round young stars. And especially in the transition disk, we hope to combine Matisse and ALMA to really have all the substructures of this disk and see if a planet can really explain this cavity and these disks. And so thank you very much for your attention.
Thank you very much for this very nice review. I learned a lot about post-AGB stars. So let me ask the first question. So we know in the planet formation community that icy grains are important because they can stick together very efficiently. So I was wondering whether there is any evidence that icy grains can exist around post-AGB stars?
We have no idea. For the moment, we don't know. But yeah, it will be very interesting to know if they exist indeed in these disks. And yeah, I mean the snow lines. I mean we can find them within the dust. So they should exist. But now we should try to observe them. Yeah, that would be nice. Yeah, indeed.
Okay, let's take a question from online. So from Gina here, most of the observed ring patterns are circular. Could they be the inner rim of detached spherical shells instead of disks?
No, we have also inclined disks. So maybe it's coming from a slide when I show. Yeah, so here, this is the same target, huh? So that's why it's the same orientation. So maybe it's coming from here, but you have some evidence for inclination, high inclination for some of the targets. So it's more likely a disk. Especially, there is also evidence for photometry that at superior conjunction, so the post-AGB star can be obscured by the disk if the disk is very inclined. So we know that it cannot be a spherical shell, so more a disk.
I just noticed there was a previous question online from René Oudmayer. I recall having observed CO 2.3 micron emission in AC HER, which might have tracing gas inside the gap. Do you have gravity data at that wavelength?
Yeah, hello, René. So yeah, we have data, gravity data at this wavelength. It's gravity. There is a master student working on this data. So yeah, it would be very nice actually to trace the gas inside the dust sublimation region, because for the moment we do not have any direct tracer of accretion. We have many indirect evidence for accretion going on, but we cannot measure the mass accretion rate as we can do for YSOs. And this is one problem. So we are looking for a way to measure this mass accretion in these systems.
Any questions from the audience? There's one from Claire. State your name and affiliation, please, once you get your mic.
Hi, Zach. This is Claire Liku. Exciting stuff. For the one target that you show that you think there might be planets, do you have enough mass in that disk to form one and survive for, let's say, a maximum of 100,000 years, or form within that time? Because I guess when your post-AGP turns into a white dwarf, then you might destroy that dust or gas that is within that ring, right?
So I'm not sure I heard the last.
Oh, sorry.
Yeah.
Sorry. I'm saying the one target you showed that you think there might be a planet there in the gap. Do you have enough mass in that ring or disk to form one? And can you do it within 100,000 years? Or is that maybe too soon?
Okay. So two questions. So yeah, so the masses of those disks as measured from ALMA, but also from our radiative transfer models are quite high in even in dust. So we can have 10 to the minus 3 masses in 10 to the minus 3, 10 to the minus 2 in gas, and so 10 to the minus 4, 10 to the minus 3 sometimes in dust. So there is enough dust to form planets. The planets that I mentioned here are not necessarily second generation planets. Actually, so far, we think that it's more likely that they are third generation planets, but maybe it's a second generation. But it can perturb the disk, as you know, and make a pressure bumps to make the dust grow in the disk. So the question is whether planets can form in such a short time scale. So by correlation alone, it will be quite difficult, but it's possible that we have a planetary embryo, a first generation planetary embryo, for example, in the disk, And when it's fed up by the second generation disk, it can grow and become a planet, for example. So you can imagine this kind of scenarios. We can also try to study this disk to know if they are gravitationally stable or not. And if they're unstable, we can form planets relatively quickly. So it's a good test, actually, whether or not this disks are forming planets to investigate that.
So a question there, Abigail.
Hi, Jacques. Thanks for such a great talk. It's really interesting results. I had a question as to the transitional disks. I was wondering, do you think it's the binary interaction itself that could be pushing these radii beyond the sublimation radius, or is there any way that would affect the behavior of these disks, or do you think it's just a photo operation or another?
No, it's the binary separation is very small. It's around 1 astronomical unit, whereas the radius of the disk is 34 astronomical units. So it's a diameter 60, 70 astronomical units. So there's no way that the inner binary is perturbing the disk. Actually, from our infrared study, the dust sublimation radius is already larger than the dynamical truncation radius of the disk. And so when you have even larger cavity, it's even less likely that the inner disk rim is perturbed by the inner binary. So we need something else to create the cavity in the dust.
Okay. And also related to that, so do you see, like, are you able to calculate any disk masses for both the filled disks and also the transition disks? And like, is there a clear difference in the properties of these two disks? Or are they all similar and one has just got the inner hole? I'm not sure.
Yeah, so we have very few disk masses, mainly from some millimeter observation, but there was no systematic studies of the disk masses. We have also some radiative transfer models, and so they are compatible with a dust mass, as you can see here, to 10 to the minus 3 solar masses, which is a lot. But yeah, we need to constrain the dust masses of this disk more precisely. But they seem so far that seem compatible with very high mass.
Cool. Great. Thank you.
Any more questions? I don't see anything online. So if nothing else, then let's thank Jacques again.